Hi, I'm Dan Ridley-Ellis from Edinburgh Napier University. Now, the longitudinal resonance method is a commonly used way of assessing the stiffness of pieces of wood. Yes, it's me again. It just occurred to me that we can use that video abstract to make another video abstract for that paper. The conditions for measuring the wood are far from ideal. I was just holding it in my hand, but I think we can do it. Let's listen to it again. Yes, I think we can work with that. Now, the first thing that we need to do is do a fast Fourier transform, an FFT of the sound. We can look at each of the hits individually, the light grey lines, and we can also take an average, the black line. There is this tall peak here, and we could start by thinking that this must be the frequency of the first mode of longitudinal vibration. But this would give it a fairly low modulus of elasticity, just 6.8 kilonewtons per millimetre squared. The timber doesn't look really like it would be that low. It has this one crack at one end, but I would expect the stiffness to be a bit higher. But the other thing, look, the theoretical calculations for the flexural minor, the green, and the flexural major, the blue, and the torsional vibration, the red, they don't match very well at all. And we have these fairly clear peaks in the spectrum. I'm assuming here a shear modulus which is about 1/16 of the modulus of elasticity, which is fairly typical for wood, but changing that isn't really going to help. So let's see if this unclear peak here might actually be the longitudinal one. That would mean a modulus of elasticity of 11.1 kilonewtons per millimetre squared, and look, now we have the theoretical calculations matching the peaks. Promising. But we don't really have anything in the spectrum for the first flexural modes, but they are probably suppressed by how I'm holding the timber, and the frequencies are low, so they might also not have been picked up well by the camera microphone. With a bit of tweaking for the shear modulus, we can get this better match. Now we have an estimate of dynamic modulus of elasticity of 11.0 kilonewtons per millimetre squared. And actually this piece was cut from the end of a bending test, and we'd done the longitudinal resonance on the whole piece initially with a Brookhouse MTG 960, and we got a value then of 10.94 kilonewtons per millimetre squared. So it either looks like this approach works, or we got lucky, or perhaps a mixture of the two. But certainly in this example, we see that it was quite hard actually probably to see the real longitudinal resonance frequency, which is partly because it was relatively short and it has been cut.